All right, let's continue our gallery of techniques in Chapter 7 with a technique called partial fractions. So start off with this example. And as it stands, this example really isn't bad. It's two fractions added, which means you can do the two integrals separately, which is nice. And for either one of these, all we really are going to need is a little u substitution. So let me focus on doing this integral first, and the other integral would be similar. But a little u substitution, u is x plus 2, which means du is going to be 1 times dx. And as I rewrite this integral into u, I get 1 over u, and dx is the same thing as du, and integration is easy. It's natural log of u, and u is the same thing as x plus 2, so natural log of x plus 2, and plus c. And we're done with that one. We do the other piece in the same way. So easy, not too bad. Imagine, though, that someone decided to be helpful, and it's going to not be helpful. But imagine that someone decided to simplify, to do the algebra thing and add these two fractions together. So they decided, let's get a common denominator here, because one fraction is always better than two, right? So x minus 6, top and bottom there, and x plus 2, top or bottom there. And when you rewrite this integral now, you have a common denominator of, and I'm going to multiply the bottom out just to be really helpful, x squared, what is that? Plus 2x minus 6x, so minus 4x minus 12. On the bottom and on the top, I'm going to get x minus 6 plus 3x, so x plus 3x is 4x. And let's see, minus 6 plus 6 is 0, so just 4x. And you're like, okay, still doesn't look too bad. Let's try a u substitution. U would probably have to be x squared minus 4x minus 12, which means du is 2x minus 4 dx. 2x minus 4 dx doesn't look anything like what's up there. And I'd actually kind of be stuck at this point. U substitution wouldn't work, and it turns out none of the other techniques that we have are going to work either. So it turns out by simplifying, we made this easy integral into a hard integral. So 7.4 is going to say, well, what if the problem you started with was this one? If we could somehow reverse this arrow and break the fraction apart into partial fractions, it would become much easier. And this is something they could have taught you back in algebra, but they probably didn't. So this is entirely an algebra technique. There's no new calculus technique involved here. The new thing in 7.4 is to take an integral that looks like this one and to turn it into an integral that looks like that one. So let's look at that idea. So I'm just going to ignore the integral signs and say my main task here is to start with a fraction like this, and hopefully turn it into two separate fractions. So the first task, as you might imagine, is to factor the bottom so you can see what the individual denominators were going to be. That part, hopefully, is not too bad for you, because your factoring skills are still good, I'm sure. Let's see, this is going to be what, x plus 2 and x minus 6. Okay, so I know on the next and crucial step, when I turn this into two separate fractions, I know the bottom of 1 is going to be x minus 2, I know the bottom of the other one is going to be x. Sorry, that's an x plus 2. X plus 2, and the bottom of the other one is going to be x minus 6. I just don't know what the tops of those fractions are going to be. I mean, I know in this case, I know it's 1 and 3, but in general, I don't know what's going to go up there. The typical notation that they use is to say some number, some other number, and they tend to use these capital letters, capital A, capital B. So we're left with an equation to solve that looks like this. So let's talk about solving that kind of equation. Let's see, I want a little more room here. So we need to solve for that A and that B, and typically one equation with two unknowns is not so solvable, but this one is going to be doable. So let's take a look at trying to solve this. The first thing to do is to multiply both sides of this equation by the common denominator. Okay, so multiply by x plus 2, x minus 6, both sides. On the right or the left-hand side, they just cancel entirely. Here, the x plus 2's would cancel, and you'd be left with the x minus 6. Here, the x minus 6 would cancel, and you'd be left with the x plus 2. So I can rewrite this as 4x equals a times x minus 6 plus b times x plus 2. And there's a couple ways you can tackle solving for a and b here. Here's the first way to try. Easiest way if it works is just to say this is not just an equation, it's an identity. It's something that's true all the time for any value of x. So let's just plug in, say, what if x is 6? What does this equation look like? And this equation turns into 24 equals, and here's the magic, a times 0 plus b times 8. Which means you can solve for b as 3. And you can do the same thing and say, what if x is negative 2? Or I pick the thing that zeroes out the other term. Say if x is negative 2, then we get negative 8 equals a times negative 8 and b times 0. And a is 1. And we get that all-important breakdown of knowing the integral is now a is 1, so 1 over x plus 2 plus 3 over x minus 6. And now, again, this is an easy integral to do. So that's our whole technique for 7-4, is just to take one fraction and split it apart into two or more fractions that it came from. So let's take a look at the general recommendation for doing this. There's a lot of ways that fractions sort of add together depending on what their denominators look like. And this is really just reminding you of how to break them apart, depending. So it all depends on what the factors are in the denominator. If you get two different, that's what distinct means, two distinct or different linear factors like we did. We got x plus 2 and x minus 6. You just break them apart, put an a and a b on the top. If you factor and you get down to the point where it's a quadratic that does not factor any further, that means you might have a linear term on top. So an ax plus b. And if there's another quadratic, a cx plus d, right? And then if there's combinations of those, basically the idea is if there's a linear, you put a constant on top. And if there's a quadratic on the bottom, you put a linear on the top. So one less degree. The only other thing we need to look at is what if there's a repeated factor? What if it's x minus 3 squared or something? Then you do one factor for x minus 3 and another one for x minus 3 squared. Because those two denominators could have added together, and the common denominator would have been the x minus 3 squared. So with those rules in mind, let's take a look at one or two more examples, which we'll do in the next video.